All right, well, welcome back from, hopefully you had a wonderful Thanksgiving break. Today is Monday, December the 1st. Unbelievable. December. We're almost halfway through this year. Some of y'all are going to be juniors, others are going to be seniors in a very short time. Wow. It's time to grow up. Okay? Now look, today is going to be a day in which we leapfrog up to try to catch up with the other classes and make sure we get to the end point that we need to be for the semester. So today we're going to be doing the entire unit on the periodic table. Okay? Today. Okay?
We have a test on this.
It'll be added to the next test.
Okay?
It's very basic stuff. Nothing super deep. Okay? So we can do this. Okay? Let's not have anxiety or panic attack before we get there. You can have the panic attack at the end of the day. Okay? But if you, now listen, I really, this goes against everything inside of me, because I know with my ADHD that I have, that I am so easily distracted. My wife teases me all the time, oh look, squirrel. Just kind of, it just doesn't take much to get me off track, as you guys have probably already experienced this year. But I need you to get your Chromebooks out, and on your Chromebook, I have posted two things. Number one, I posted the exam study guide. Okay? It's going to be 50 points. Optional. Okay? So, but it has to be on a separate, it's going to probably take you way more than one sheet of paper, because it's 50 points because it's a lot. Okay? I need good answers, not just, phrases, if you want to get your points. It's going to be due next Friday, Friday the 12th. I will post answers that evening. The exams start the next week. Okay? I think they start on Tuesday, don't they? Oh, that is Tuesday, Wednesday, Thursday, Friday, I think, are exams. Is it Monday through Thursday? No. It's Tuesday through Friday. So we'll still have Monday to kind of review any questions. Okay? So Friday and Monday are review days. Okay. So here we go. So the second thing is I posted this. Okay? You have this periodic table. Now this periodic table has all the entire first half of the unit right here as far as what you need to know on this. Okay? So when we're looking at this, this is going to be important. So we're going to go old school though. And I'm not giving you any notes, written out notes. I'm going to actually write all the notes on the board. And you're going to have to do this crazy thing called just take notes on a piece of paper. Oh no! First day back. But most everything that we're going to talk about for this first part, again, can be deduced. If you need paper, there's some, or you can just go. Way to come to class prepared. You need paper every day. But here's the problem, is that you give it to him every day, so you enable him to be irresponsible. You need to say, no, get your own, and he'll have to just write it on his arm for the first day or something.
Well, I got a notebook, but I lost it.
That means you don't have one. That means you had a notebook. All right, here we go. So here we go. The first part of this is going to be just learning the classifications of the periodic table. Okay? So it's all the classifications are all right up here. They're already given to you. I'm just going to go through them quickly just to kind of explain and give you a little bit of the background and the nuances of it. Okay? So first off, columns. What are columns called? Groups or, I heard somebody say it, families. Groups or families. Why would they be called families? You just had Thanksgiving. Similar what? Well, what characteristics? Similar chemical what? Properties. Similar chemical properties. Now, why though do they have? Let's relate back to we just talked about electrons. Why would they have similar chemical properties? Is this? Are you getting all this over here? One job. Do I need to call in the, like the commercial? I need the replacement. You've seen that commercial where the kids won't take the picture and they have to, the backup or okay. Why? Listen. Why would they have similar chemical properties?
Because they're like the last electron is in the same.
Oh, perfect. Okay. Okay. Somebody explain that though. Okay, go ahead, Anderson. You can explain even more. When you look here at lithium, okay. When you look here at lithium, where's the last electron?
In S2.
2s1, right? Where's the last electron in sodium? 3s1, 4s1, 5s1, 6s1, 7s1. So they all have one electron in their outermost energy level. They have a similar outer shell. And what's the word for that? Electrons in the outer shell. I just heard something. The valence electrons. Okay? So they have similar chemical properties because atoms in the same family have the same outer shell, which we call the valence shell, electron configuration. I'm just going to abbreviate. If I say config, you guys know that that's configuration.
Yes, sir.
Okay? Does that make sense? So, if we look at beryllium and magnesium, they're all going to have how many electrons? Where are their outer shell electrons? S2, right? 2s2, 3s2. So they're going to have the same outer shell electron configuration. Now, here's something. The outer shell is not the outer orbital. It's the outer shell is an energy level. Okay? So when you come over here to boron, okay, how many electrons are in the outer shell? Okay, there's one in the P, but in the outer shell, the outer energy level, there's going to be 3. So boron, this whole family is going to have 3 valence electrons. Because the big confusion is that the valence is not the outer orbital, it's the outer shell, the whole energy level. Now only S and P electrons are going to be valence electrons. Because by the time you get to 3D, what is potassium and calcium? Where are their electrons going to be? 4s, right? So the D's don't fill until after the S. So you have 4s, 3D. So that 3 is not the outermost energy level. 4 is the outermost energy level, right? So the D's and the S, because of the overlap, the D's and the F's are never the outermost energy level. Only S's and P's are going to be valence electrons. So if you want to even just do another thing here, this is only S and P electrons. Okay? Because the D's and the F's don't fill, the 3D doesn't fill until 4s has already filled. You following me on that? So when I'm looking then on the periodic table, I'll just go up here so you can just show here. So these, okay, this is all, how many valence electrons is everything in this family going to have? 1. This family is all going to have 2. Now these groups all kind of do different things. It's 3D. Remember, the D's don't have valence. So here, these are all going to have 3. So it's family 13 is going to have 3. Family 14 is going to have 4. 15 is going to have 5, 6, 7. Oh, 6, 7, and 8. Okay? So we can know the number of valence electrons. Now, valence electrons are very important because when we do our next unit starting tomorrow, it's going to be all about bonding. Is the valence electrons are the ones that are involved in bonding. So they're the ones that we're most concerned about. So we need to know how many valence electrons there are. So it's real easy. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now again, S and P, well, how many electrons total can be in the S? How many electrons total can be in the S sublevel? 2. How many total can be in the P sublevel? 6. How many is that up to? 8. That magic number 8. Okay? Now, so that's our columns, or our groups or families. They're called families because they have similar chemical properties. You're with your family, and it's sometimes, as much as you hate to admit it, you're similar to your brothers and sisters. You're similar to your parents. You know, I vowed, you know, sometimes say I'm not going to do this. I find myself doing things just like my dad did, you know, even though, anyway. So we end up having those family characteristics, and oh, you resemble your brother, you resemble your sister, you look just like your mama, you know. So we have those characteristics, but it's because they have the same outer shell, valence shell electron configurations. All right, so now we look at the names. Okay, we want to name the families. Family 1A are known as the alkali metals. Does anybody know what does the word alkali mean? No. That's the next column is Earth.
Is it something to do like water?
Not really. They talk about some waters. They talk about being alkali.
Yeah.
They have alkaline batteries, but the word alkali. No. Are you looking it up? Yeah. No, I wouldn't do that. Okay, alkali means basic, as opposite of acids. You have acids and bases. Alkali means if something's alkaline, that means it's basic. They call these the alkali metals because all bases, well, not all, well, yeah, what makes a base is the presence of the hydroxide ion, the OH minus ion. So lithium hydroxide, sodium, potassium, rubidium, cesium hydroxide, those all make very strong bases. Okay? Soaps are made out of lye, which is sodium hydroxide. Strong base. So alkali means basic. So they're called alkali metals because they form strong bases when combined with the hydroxide ion. Group 2 are known as alkaline earth metals. Alkaline earth metals. They too make bases. Now these aren't real soluble, but I don't know if you've ever heard of milk of magnesia. It's magnesium hydroxide. It's used as a medicine. It's an antacid. Well, what do you think an antacid is? What's ant mean? Opposite. What's the opposite of an acid? A base. So rather than saying magnesium hydroxide is a base, they call it an antacid tablet or an antacid because magnesium hydroxide will neutralize your stomach acid. It's a base. It's not soluble in water though, so it's chalky, so it looks like milk. Okay? But strontium and barium hydroxide are very strong bases. So these two are bases when they're with the hydroxides. Okay? We don't name, we're going to come back on this one. None of these have names until we get to the oxygen family. Now, that's not on here. The oxygen family isn't listed as a family, but group 16 are known as the chalcogens. Very few people know that. That's not a common name. And I've looked it up before, and I always forget what chalco means. Gen means forming, but it's forming some kind of compound is what that comes from. What's the name of group 17? It's the halogens. Okay, that's on there, but the 17 are the halogens. You may have heard of halogen headlamps in a car. Okay, halogen light bulbs, halogen flashlights. They put those gases in there. They make very bright lights. Okay. But this halo, this means salt forming. Gens means forming. Halo is salt forming because sodium chloride, they're the ones that make salts. And then group 18, what do we know group 18 is called? Noble gases. Now why do you think they're called noble gases?
They don't react.
Okay, so why what would they call that noble then?
They're above
Because their energy levels are filled, okay, that's why they're inactive. But they're called nobles because they don't associate. The nobles, I call them the stuck-up gases. Because they're too good to associate with the other common folk elements, you know, so they're the nobles, because the nobles then associate with the common people. So the nobles don't react, and so another name for them are the inert gases. What does the word inert mean? Non-reactive. They don't react with anything. Helium, neon, and argon, there are no known compounds with helium, neon, and argon. Helium, neon, and argon's total existence in the world is a single monetary, by themselves, atoms just floating around. They don't even hang out with each other. They don't even bond with each other. Only single atoms, okay? Just shows you money can't buy you love. Okay, just because you're noble, okay? They're still just live a lonely, by themselves life. Okay? They don't bond, there's no known compounds with helium, neon, and argon. Now, krypton and xenon, under very strenuous conditions with the most reactive fluorine and chlorine, they can form a few compounds, but they're still pretty much non-reactive. So they're called inert gases. Now, by far, noble gases is the most common name. And then another even less common, they're called the rare gases. That's really old school, but so noble gases is by far, and that's what we'll refer to them as noble gases. Okay? All right. So that's your columns. Okay? What are your rows called?
Periods.
Or periods or series. But generally periods. Now why are they called periods? Well, why is it called the periodic table?
because the chemical properties occur periodically.
Because the chemical, so what does that mean they occur periodically? What does the whole term period mean here? What? No? It means every so often. Okay, all of y'all watched the video, right? Okay, even if you didn't, shake your head yes so I don't get frustrated. Okay? You saw that lithium, the best part of the video, they put lithium in the water and it buzzed around on the top. But then if you put beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, none of them react with the water. But then you go and you put sodium back into water, and sodium metal then began reacting with the water. But then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon did not react with the water. But then you put potassium. This is the one that caught on fire, and it burned with a lilac flame. Okay? And then none of these did, and then rubidium did, and then finally cesium is the one that blew up the whole thing. And I actually just got someone's willing to donate some cesium to the school. I've never seen it in my life, you know. It might be a good, let's blow up the school and then retire. So I don't know. I'm very hesitant to get that because you can see, and I don't even know how much they put in there. Huh? Some guy is willing, has some, and he said he'd donate it to the school. It's in a sealed vial, but I don't even know how much they put in. Didn't look like they put in very much to see the explosion of that. Okay? So the whole point is, listen, the whole point is that this family has a unique set of chemical properties based on its electron configuration. Well, those properties repeat themselves every so often, periodically. back in the day, before the internet, when I was your age and I had to do a research paper, we had to actually look up the information in encyclopedias, but in periodicals, in magazine articles, in newspaper articles. So we would go to a library and they would have the periodical room. I think that, does our library even, doesn't it have a periodical at the very back? Doesn't it say the periodical room? It used to. You guys never even go back that way. It's back by where the computers are, those two computer labs are. There's a room in the very back there. I think it's labeled periodic. Okay, but we would have to go and look up articles in magazines and in newspapers that related to the topic that we're doing our research paper on. We didn't just say, hey Siri, or hey chat, give me, write a paper about this for me. We had to go into the periodical because the magazines came out once a week, once a month. Okay, the newspapers came out every day. They came out periodically. Okay, just go anatomical. That's again why the woman's period is called a period, because it's a cycle. It repeats itself every so often. Okay, but that's just a period. When you get to the end of the row is when the chemical properties begin repeating themselves. The end of the period. Okay, all right. Now we're gonna listen. We're gonna call almost all these are called period. The only time we're gonna use the term series is on these bottom two rows. And by the way, this is the more traditional periodic table, where you have lanthanum and actinium here. Okay, notice here that they have the lanthanum activity up here because they're assuming some experimental evidence shows the electrons do some weird things. One goes into D before they begin filling the F's, and then they go back all into the F's. They do some weird shifting, okay? But the traditional one is here, to where the lanthanum fills in here, so they call this the lanthanide series, and this is called the actinide series, the row, okay? But usually we just refer to the rows as periods. All right, so that's our columns and rows. This all green section here are known as your transition metals. This is your D block of the periodic table. They're called transition metals. These down here, I don't know, I've never seen this term before. So if you were to print this out at home or whatever, we're going to call the bottom two rows the inner transition. I-N-N-E-R, inner transition metals. Okay. Now, another name for them. Does anyone know another name for those bottom two rows? Anybody heard? You've heard of it once. I'll write it. The rare earth metals. Rare earth metals. Now, this is super important that you just know that. If you've been following the news at all, you'll hear the term rare earth metals. They're used a lot in making batteries for cars, heavy duty electric batteries. They use the rare earth metals. They're necessary for that. Cell phone batteries use some rare earth metals in them. Right now, most of the rare earth metals that we use come from China. Well, we know that our political situation with China is very tenuous. So one of the deals that Trump was trying to make with Ukraine, when Ukraine's fighting Russia, Ukraine is using all American war machine stuff. And so President Trump was trying to make a deal to where, okay, well, we'll sell you this war equipment, the missiles and bombs and all that stuff, if you will give us rights to, they have a bunch of rare earth metals in Ukraine. So that would take some of our dependence off of China. And so they're trying to constantly negotiate some of those things as far as getting the rare earth metals. I read somewhere not too long ago that they may have found a big stockpile of those things in Montana, up in that area, that we might have some rare earth metals there. Okay, so you'll hear that term a lot. Now the rare earth metals really only, I can just naturally go there. This row is really your rare earth metals, because these down here, and if you look, Most of those, they're all radioactive. They're not going to be used in batteries. The top row are really the ones that are going to be rare earth. This magnet right here, this is a neodymium magnet. It's a much stronger magnet than a normal ferromagnet, than one of these type magnets. Okay, neodymium is element number 60. They're used for very strong magnets. So transition metals, they're called inner transition metals because they go inside here. Okay? All right. So that is all of the groupings that you need to know. Now you just need to know those, but you need to know the names. You need to know the main elements. Also, one other thing is here, the main group elements. That's not listed up there. They're sometimes called main group. Okay, those are your S and P groups. Okay, so what does that mean? That's going to be groups 1 and 2. And then what other groups? What other groups have your S and P sublevels?
13,
13 through 18. Okay, we call those your main group because those are your S and P. Those are the ones with the valence electrons. Those are the ones that we focus in on bonding the most. All right, so most all of that's on this periodic table. I just wanted to kind of fill in some of the other little gaps there. We good with all that? Okay, I probably, if I were you, I'd print this out when I got home and just try to have this with me rather than just keeping it on your Chromebook, just so you have all that. You can just look at it. That would be my recommendation. That's a lot of color prints for me to make for you. All right, good deal. Does everybody have everything written down? I'm about to erase it all. Has everybody got it? Did you want it? Going once? We're good? Y'all, and just so you know, for the first, I would say for the first 30 years of my teaching career, I wrote all notes on the board. I never gave out any handout notes. We would just do this all day long, and you just have to take it. Okay. Now, this is the important part. What can we tell about an element based on its position on the periodic table? Periodic trends. And we have to look at 3 of them before the bell rings. No problem. Periodic trends. The first trend is atomic radius. What do you think happens to the size of the atoms as you move down in a family and why? Okay? So you staying with me? Sure looks like that Chromebook is not probably on that periodic table. All right, that's why I don't like to have that out anymore. So now, actually, let's do this. We can now focus here because we're done with looking at this. So let's go ahead and put the Chromebook away, okay? Because I know that it's just, and I'm just as guilty. I mean, I would just. I take a class every Tuesday night, and when I'm in class, I have a computer open. I'm trying to follow along with it, and I tend to find other things to look at.
What class do you take?
It's just it's at the Bible College.
Oh.
And so,
You still do school?
I still do school. Lifelong learner, baby. Lifelong learner. I was watching. My wife was teasing me last night because I was watching videos on quantum mechanics last night on my phone, just for fun.
So you're gonna be like Einstein or something, right?
He is not.
God did not bless me with that brain. But I'm trying to use as much as I can and understand as much as I can. What is, first off, simple definition, atomic radius. What does that just mean? In a simple sense, the atomic radius, we're measuring what? The radius, but what's a different word that we could use other than radius? Thank you very much. Say what?
Size.
The size. How big is the atom? The atomic radius. We're going now, here's the issue. We're going from the nucleus to the outer edge of the electron cloud. Well, is the electron in an orbit around the nucleus? What did we learn? What are these red things called? Orbitals. What's the definition of an orbital? The most likely place. But is the electron confined to that space? Do we know where the electron is actually in that space? Remember, we just made the shape where there was a 90% probability of finding the electrons in that space? So that means the electron's going to be out here, so the outer edge of the electron cloud is very fuzzy. So it's kind of hard to get the radius. So they take the nucleus of this one, the nucleus of this one, and they just get the distance between them. Okay, how far between are they, those two? That's going to be your atomic radius, your covalent radius. Okay. Now, as we go down in the family, what do you think happens to the size of the family and what? Okay, I just heard somebody say what? Does it get bigger or smaller, you think, going down? This is not some big, mysterious question. It gets bigger. You have 3, 11, 19, 37, 55, number of electrons. But what's the outer shell electron configuration for lithium? 2s1. What about sodium? 3s. What does that 2, 3, 4s, 5s, 6s1? What does that 2, 3, 4, 5, 6 represent? Say that again. Energy level. Okay. Some enthusiasm. Come on now. I'm the only one that's excited in here. Okay. They're the energy levels. So what do we know? Are the energy levels all the same distance from the nucleus? Everyone's a little bit farther away, right? So what happens to the size of the atom as you move down in a family? Okay? So it increases going down in a family. Because each new element how would I finish this? What?
Like has another energy level?
Perfect. Has you said another, I'm going to say an additional. Energy level. You're just adding another layer to the onion every time you go down. The second row has 2 energy levels. The third row has 3 energy levels. So obviously as you add an energy level, the atom gets bigger. Well, what about going left to right across the periodic table within a row? As you're going from lithium to beryllium, boron, carbon, nitrogen, what's happening? You got more electrons, right? But are they going in different energy levels? And as long as you're in the same row, they're all going the same energy level, right? So are the electrons adding any size? What? But if you're adding electrons, what else is increasing? What? What equals electrons? Protons. Remember that the attraction is protons in the nucleus to the electrons, and that's what holds them in. So as you go left to right, the electrons are all going the same energy level. So they're not making it any bigger. But the nucleus has more protons. That's the magnet on the inside. So it actually pulls the electron cloud in a little bit more tightly. So the size actually decreases. Decreases going left to right within a family, within a row, a period, because the electrons are all on the same energy level. But each new atom has one more proton, which pulls the electron cloud in more tightly. Now, if you want to see that pictorially, you can look at that like that. So we can see, as you move down in the family, what's happening? It gets bigger. Now notice, remember, are our energy levels evenly spaced? Remember, there's a big gap between the first and the second, right? And then the gaps started getting smaller, and the farther out they got, the closer they got together. So notice the big difference in size between hydrogen 1s1 and lithium 2s1. Big difference in size. And then there's a relatively big difference between 2 and 3. But the difference gets smaller and smaller because the energy levels are getting closer and closer to one another. So when you add the next energy level, you're not adding that much more size. So, but they get bigger going down because you're adding another energy level. And then notice you can see very easily here that they're getting smaller left to right. Because as you're going here, all of these extra electrons are all on the second energy level. The S's and the P's aren't that much farther apart. But more protons pulls the electron cloud in more tightly, so they get a little bit smaller. Now this trend is very important because the next trend is going to be based upon it. Good? That makes sense so far? Still nothing super heavy. Okay? We got this? All right. So the second trend is ionization energy. Which is defined as the energy needed to remove an electron from a neutral atom or an ion. I'm working with them. Am I just getting hot, or is it hot in here? Are you guys all comfortable? It's comfortable? Okay, it's just me. You're just getting fired up. All right. So now let's think about this. In terms of this, as we go down, now first off, ionization energy. So if I have electrons, if I'm going to compare 1s2, 2s1 to 1s2, 2s2, 2p6, 3s1, which electron do you think is going to be the first one to be removed? The one in the 1s, or the one in the 2s, or the one in the 3s here? I mean, in this atom, which one do you think is the first one out? The 2s, because it's farther away, right? The 3s1 is the one that's farthest away, the least tightly held. Now, which one do you think is more tightly held? The one that's here, or the one that's here, farther away? This one's more tightly held, right? So it's going to take more energy. This one gets a little bit easier. Remember what, when we watched lithium, sodium, potassium, rubidium, cesium react with water? They were all losing that outermost electron. Well, which one lost it the most readily, the quickest, the most energetically? Well, the cesium did, because the electron was farthest away, easiest to remove, and so it just, bam, it just reacted all at once and blew up the whole thing. Okay? So that means that this is inversely proportional to the size. So what does inversely proportional mean? Opposite. So as the size gets bigger, what happens to ionization energy? It goes down. So then underneath this, I'm going underneath here, so A underneath here. So going down in a family, well, let's just say, does it increase or decrease going down in a family? As the atom gets bigger, what happens to ionization energy? Decreases going down in a family. And then left to right, what's going to happen? Increases. Left to right. And then if you need to, I mean, the atoms are getting bigger, so it's easier to remove. Atoms getting smaller, so it's tougher to remove. Third one. I got 4 minutes. The oxidation state is the number of electrons, an atom tends to gain, lose, or share when bonding. This is what we talk about with ionic bonding. This really is more covalent bonding. We're really going to pretty much just talk about this one right now. When we get into bonding, starting tomorrow, we'll start looking at the sharing part. But what was the magic number you guys learned about in middle school as far as the electrons they want to get? Go ahead, Anderson, what?
8.
8. Follow me. Okay? So when I look here again, okay, when I look here, these all have 1s, so it's 2s1. They want to be like a noble gas. The noble gas configuration is the stable configuration. So lithium can either gain 7 and become like neon, or it can lose 1 and become like helium. So which is easier? Lose 1. Okay? So all of these have 1 electron in their outermost energy level, so they're going to all tend to lose 1 electron, form a +1 ion, when they bond, because then they can all have this noble gas configuration. So we would say that the oxidation state then of the group 1, the alkali metals.
Mr. Hobbs?
Yes.
Can I get Bailey Mankus to the front office, please?
Sure.
Thank you.
Just take all your stuff with bills without them. Okay? So it's going to be +1 is the oxidation state. Well, these all are going to be what? Is you either lose 2 or gain 6. Lose 2, so they're all going to be +2. And if you look on the periodic table that I gave you, the one like this, there's a little number 1 and a little number 2 above the symbol, and that's its oxidation state. It tells you that what it is. Now the transition metals, just stay with me, we got 2 minutes, and I'll be able to finish here in 2 minutes. Okay? Okay? So the transition metals do all kinds of different things, and they have a plethora of possible oxidation states. Okay, we'll talk about that when we get into bonding. Okay? But the boron family can either lose 3 or gain 5, which is easier. So they're all going to be +3. There's a little number 3 above all of these. So when they bond, they tend to lose 3. Now, the carbon family, lose 4, gain 4, it could be either way, so we'll say plus or minus 4. But nitrogen now, it can either lose 5 or gain 3, which is going to be easier. Gain 3. Well, when you gain, you get a negative charge. So it's -3, -2, -1. So the trend in oxidation states is +1, +2, +3, plus or minus 4, -3, -2, -1. Now that's going to be humongous, very, very important for you to know that, again, when we do bonding. because that's going to tell me how many they're going to gain or lose. That's going to determine the formula of the compound. That's going to determine how it reacts and how it bonds. Okay? So that's what you need to know for right now. Tomorrow, I may jump in and just kind of show you one other little thing about ionization energy in terms of size of the ions and, you know, one more trend, just kind of look at briefly, and then we're going to start in on bonding. This is what everybody wants to know, how things react and how they bond, and we'll have labs for that. All right, you guys have a great day, and go Jags.